Hello everyone, I'm Said and welcome to this masterclass on Riemann sums. If you've ever looked at a graph of a function and asked, how do I find the exact area under this curve? You are asking the same question that led to the development of integral calculus. The core idea is simple. We can't measure the area under a curve directly, but we can measure the area of a rectangle. So if we break the area under the curve, for example like this or like this, or into thousands of thin rectangles, we can approximate the area. The sum of the area of these rectangles is what we call a Riemann sum. Now the question is, how tall should our rectangles be? Look at this graph. If we want to be sure we are underestimating the area, we take the lowest point of the function in each subinterval, like this, here, and here. This is the lower Riemann sum. And if we want to be sure we are overestimating the area, we take the highest point of the function in each subinterval, like this, or here, right? This is the upper Riemann sum. Let f of x be a function on the closed interval a to b. We divide this interval into n subintervals of with delta x equals b minus a over n. So lower sum means L sub n equals the sum of minimum value of f on x sub I minus 1 to x sub I times delta x from I equals 1 to n. And upper sum means u sub n equals the sum of maximum value of f on x sub I minus 1 to x sub I times delta x from I equals 1 to n. So for lower sum, we can say the lower sum provides an underestimate of the area. And from the upper sum, we can say the upper sum provides an overestimate of the area. And the true area is trapped between the lower and the upper sums, right? But pay close attention here. When n the number of rectangles, for example, in this curve n equals 5, 1, 2, 3, 4, and 5, right? When n the number of rectangles is small, there is still a lot of empty space, like here, and here, and the approximation is not very accurate. But as n gets larger and larger, like this for example, the rectangles become thinner and thinner and they start to match the shape of the curve much better. Now that you've grasped the basic concept of Riemann sums, let's dive a bit deeper. As you can see in this diagram, we are using 3 rectangles to approximate the area, which means our n is equal to 3, right? Also remember the fundamental rule. The area of each rectangle is its width times its height. The width is delta x. So, for example, here is a, so x1 equals a plus delta x, x2 equals x1 plus delta x or a plus 2 delta x, and b equals a plus 3 delta x or x2 plus delta x, right? And the height is the function value f of x at a specific point. Now let's examine how this changes when a function is increasing versus when it's decreasing. Let's look at the first case where the function f is increasing. In this graph, we use the right endpoints, means here, this, and this. Since the function is increasing, the right side is the highest point. For example, in this interval, we choose x1, means a plus delta x. And in this interval, we choose x2, and in this interval, we choose x3. This results in an excessive approximation, means overestimate, where the rectangles exceed the curve. So we have upper estimate means un equals the sum of f of xi times delta x from I equals 1 to 3. Or in this graph, we use the left endpoints, means this, like this, like this, means x sub I minus 1 to determine the height. Because the function is climbing, the left side of each subinterval is the lowest point. For example, in this interval, a is the lowest point, and in this interval, x1 is the lowest point, and in this interval, x2 is the lowest point. This gives us a deficient approximation, means underestimate, because the rectangles stay below the curve, right? So lower sum means ln equals the sum of f of xi minus 1 times delta x from I equals 1 to 3. Now let's see what happens when the function f is decreasing. The rules of the endpoint are now reversed. For a decreasing function, the lowest value in each interval is at the right endpoint, means here, here, and here. Using these points gives us the deficient approximation. So in this case, right endpoint is xi. So ln means lower sum equals the sum of f of xi times delta x from I equals 1 to 3. And in this graph, to get the highest possible rectangles, we must use the left endpoints, means xi minus 1, as they represent the maximum value in a decreasing slope. So we have upper sum means un equals the sum of f of xi minus 1 times delta x from I equals 1 to 3. To conclude, we can see a clear pattern. For an increasing function like this, left endpoints give the lower sum and right endpoints give the upper sum. And for a decreasing function like this, right endpoints give the lower sum and left endpoints give the upper sum. In all cases, the true area under the curve is trapped between these two sums, means ln is less than or equal to the integral of f of x dx from a to b is less than or equal to upper sum. As we increase n means the number of rectangles, these two values will eventually converge to the exact integral. For example, if f of x equals 2x plus 1 on the closed interval 0 to 3 and let n equals 3. Since f of x is increasing, the lower sum uses the left endpoints and the upper sum uses the right endpoints, right? So delta x equals b minus a, 3 minus 0 over n over 3 equals 1. So the partition points are 0 to 1, 1 to 2, 2 to 3. So the lower sum means L3 equals, as you know, the lower sum uses the left end points, means 0, 1, 2. So we have f of 0 plus f of 1 plus f of 2 times delta x means 1. So we have f of 0. If we plug in 0 for x, we have f of 0 equals 1. Equals 1. F of 1, if we plug in 1 for x, we have 3. 2 times 1 plus 1 is 3. And f of 2 equals 2 times 2 plus 1 equals 5. Equals 5, right? So L3 equals 1 plus 3 plus 5 equals 9 times delta x. Delta x equals 1. So L3 equals 9. And for an increasing function, the upper sum uses the right endpoints, means 1, 2, 3. So we have the upper sum equals f of 1 plus f of 2 plus f of 3 times delta x. So u3 equals f of 1 equals 3 plus f of 2 equals 5, and f of 3, if we plug in 3 for x, we have 2 times 3 equals 6 plus 1 is 7 plus 7 times 1, right? So we have 15. So final answer is lower sum equals 9 and upper sum equals 15. So for this increasing function, the lower sum underestimates the area and the upper sum overestimates it. Number 2, if f of x equals x squared on the closed interval 0 and 2, let n equals 4. First find the width of each subinterval. Delta x equals 2 minus 0 over 4 equals 1 half, right? So partition point is 0 to 1 half, means 0 plus 1 half, and 1 half to 1 half plus 1 half is 1, and 1 plus 1 half is 3 over 2, and 3 over 2, and 3 over 2 plus 1 half is 2, right? So since the function is increasing on 0 to 2, use the left endpoints, means 0, 1 half, 1, and 3 over 2. So L4 equals f of 0 plus f of 1 half plus f of 1 plus f of 3 over 2 times delta x times 1 half, right? So f of x equals x squared. So f of 0 equals 0. F of 1 half equals 1 over 4 or 0.25. F of 1 equals 1, and f of 3 over 2. F of 3 over 2 equals 9 over 4 or 2.25. So L4 equals f of 0 equals 0 plus f of 1 half equals 0.25 plus f of 1 plus 2.25 times 1/2 times 0.5. So we have 1.25, right? And U4 equals, use right endpoints, means 1/2, 1, 3/2, and 2. So we have f of 1/2 plus f of 1 plus f of 3/2 plus f of 2 times delta x, right? So f of 1/2 equals 0 to 5. 0.25 plus f of 1 equals 1 plus f of 3/2 equals 9/4, or 2.25 plus f of 2 means 2 squared equals 4 times 1/2. So we have, sorry, this answer is 1.75. So final answer is 3.75. So final answer is L4 equals 1.75 and U4 equals 3.75. Number 3, f of x equals 5 minus x on the closed interval 0 to 4, let n equals 4. Since f of x is decreasing, the rules are reversed, means lower sum uses the right endpoints and upper sum uses the left endpoints. So first delta x. Delta x equals b minus a. 4 minus 0 over 4 equals 1. So the partition points are 0 to 1, 1 to 2, 2 and 3, 3 and 4. And as you know, for a decreasing function, the upper sum uses left endpoints, means 0, 1, 2, 3. So upper sum equals f of 0 plus f of 1 plus f of 2 plus f of 3 times delta x, and the lower sum equals, uses right endpoints, means 1, 2, 3, 4. So f of 1 plus f of 2 plus f of 3 plus f of 4 times delta x. So we have f of 0 is 5, f of 1 is 4, f of 2 is 3, f of 3 is 2 times delta x means 1. So the upper sum is 14 and the lower sum is 10. That's it. It's very, very simple. Or f of x is 1 over x on the closed interval 1 to 3, let n equals 2. F of x is decreasing on this interval, so we use right endpoints for the lower sum and left endpoints for the upper sum. So we have delta x equals b minus a, 3 minus 1 over 2 equals 1. So the partition points are 1 to 2 and 2 and 3. So upper sum means u2 equals, use left end points means 1 and 2, means f of 1 plus f of 2 times delta x. So we have f of 1 is 1 and f of 2 is 1 over 2 or 1 half. So 1 plus 1 half is 3 over 2, and the lower sum means L2 equals f of 2 and f of 3. F of 2 plus f of 3 times delta x times 1. F of 2 is 1 half plus f of 3 is 1 over 3 equals 5 over 6. So U2 is 3 over 2 and L2 equals 5 over 6.